All right, guys, three more examples of Lewis structures in this video, okay? So here we go. First one we're gonna do is oxygen, okay? Diatomic oxygen. Calculate number of valence electrons. Oxygen is a chalcogen, it's 2 away from the noble gases, has 6 each. There's 2 of them, so it's gonna be 12 valence electrons. So we're gonna draw a skeletal structure, connect them, and now start splitting them. So we've used up 2 electrons in that single bond. We have 10 left because we have 12. 2, 4, 6, 8, 10. That's it. 10 left, right? Total of 12 in here, counting the double bond. Is this following the octet rule for both the oxygens? 2, 4, 6, 8. That oxygen, yes. This oxygen, 2, 4, 6, no. Only 6, okay? So that's telling us we're gonna have to move one of these double bonds, one of these lone pairs into a double bond. And that's gonna be our Lewis structure. 2, 4, 6, 8 for this oxygen. 2, 4, 6, 8 for this oxygen. Octet rule satisfied, okay? So that's that one. Next one, another covalent compound. How would we name this? Dinitrogen Difluoride, right? Don't forget your naming rules. All right, so what are we gonna do here? Well, we have 4 atoms, and we know our least electronegative atom is the center atom. So fluorine is the most electronegative element. So we're gonna put the nitrogens, therefore the least electronegative one, we're gonna put those in the center. Something like this. By the way, we forgot to calculate the valence electrons. We could do that first. So nitrogen is 3 away from the noble gases, has 5 valence electrons. So it's 2 nitrogens, and there's 2 fluorines. Fluorine is a halogen, 7 valence electrons. So that's a total of 10 plus 14. That's 24 valence electrons. Okay. So let's connect our structure here that we have. And let's start now adding in a uniform fashion, right? Equally distributing all the electrons that we have. We put down 2, 4, 6. So 24 minus 6, that's 18. So I have 18, I'm going to count. 2, 4, 6, 8, 10, 12, 14, 16, and I'll just say 18 here, okay? Let's see what's following the octet rule or not. 2, 4, 6, 8. Fluorine's good here. Nitrogen, 2, 4, 6, 8. Nitrogen's good. Nitrogen here, 2, 4, 6, 8. Nitrogen's good. Fluorine here, 2, 4, 6. Not good, right? So we're gonna have to add a double bond here. That's what that's telling us. So let's remove a lone pair. Where do we want to remove it from? If we remove it from here, that's not good. That's making fluorine even worse. So we want to remove it here. We want to add, if we add to fluorine, will that help? And so let's see. So if we do something like that, that would be fine. Okay. Now, later in the course, we'll talk about formal charges. And it turns out this isn't super stable this way. But according to our octet rule, 2, 4, 6, 8, that's good. Here, 2, 4, 6, 8, that's good. Okay. We'll talk about something called formal charges, which will tell us this Lewis structure isn't super stable. And so you can go through this and you can actually draw a different Lewis structure. I'm gonna redraw this. Okay. And this time I'm gonna keep the fluorines, the nitrogen fluorine bonds to be both be single. Okay. And we have 24 valence electrons. And so I have, let's see, 2, 4, 6, 8, 2, 4, 6, 8, that's 16. And then I have 18, 20. and I'm going to make an octet there, 24. That turns out, so that's octet rule, 2, 4, 6, 8, right? 2, 4, 6, 8, 2, this nitrogen, 2, 4, 6, 8, this fluorine, 2, 4, 6, 8. That turns out to be the best structure. These are both in resonance, technically, just like we talked about with the carbonate anion in a different video. But it turns out this one is more stable because of formal charges. So let me just write that. More stable because of something called formal charges. And we'll talk about this later in the chapter as to why, but you would want to report this as your answer. This is the most important resonance structure. This one's still valid, okay? It's just not as good of a reflection of reality. Okay, so let's clear that one and let's do one more. HCN. Okay, so least electronegative atom. Well, let's first do our valence electrons. 1 for hydrogen, 4 for carbon, 5 for nitrogen, 10 valence electrons total. Least electronegative one, carbon's on to the left of the periodic table of nitrogen, so it's going to be less electronegative. So carbon's going to be in the center. Hydrogen, remember, is never going to be in the center. And so we're going to have something like this as our skeleton with the single bonds. We have 4 electrons down there, 2, 4, 2 in each bond. We have 6 valence electrons left to pair out. Hydrogen's happy, it's a duet rule, or it has 2. So let's pair out the other 6. So that's 10, right? 2, 4, 6, 8, 10. That's our 10. And this isn't happy because we have 2, 4, 6 only for carbon. We need 8. And we have 2, 4, 6 only for nitrogen. So again, we're going to have to do some double bonds. And so let's add a double bond there. Let's check it now. Hydrogen's still good. Carbon is not good. It only has 6, 2, 4, 6. Nitrogen has 2, 4, 6, 8. So nitrogen became good. So, but again, we're out of electrons. So we're going to have to make another bond here. So we're going to make a triple bond. And now let's check it out. Hydrogen has 2 still. Carbon has 2, 4, 6, 8. That's good. Nitrogen has 2 in the lone pair, 4, 6, 8. So that's the final answer. All right, so that was our last practice problem. Keep practicing these guys. It's not super hard, but you know, it does take practice. And let me know if you're having any trouble with this.